Well, good morning, everybody. This is Mathman. And before we move on to our topic, I just wanted to mention about the marvels of science. And yesterday I had a catheter put in my wrist to have my heart checked out. I was having symptoms for about a month. And it turned out that I had two blocked arteries. And so they stented them, and within a few hours, I'm back home again. that's that's amazing. 30 years ago, I would have been getting a heart bypass surgery. I would have been in the hospital for a week. Um, I would have been recovering over the course of a month. And now they have you going in and out and done within a few hours and back at home. And one of the things that they do is they take fractal dimensions while they're inside your vessels. It helps them understand the degree to which you have arterial disease and how extreme the blockages are. So I think that's kind of fascinating because that's pure mathematics. And so, in a sense, mathematics saved my life. So, before I go much further, um, this video is going to deal with exponents and what we mean by being in a base, base 10, base 2, base 5. There are all kinds of counting systems, and the counting system that we use is base 10, and we'll get into that. It's really fascinating stuff. So, uh, before I go on to too much of a tangent, I just did something to my screen that I didn't want to do. There we go. So, um, let's get to it. Okay, so we know what it means to add. That when we have 5 plus 1, we know it's 6. And it's basically a form of counting. If we had one widget and then we had 5 more widgets and we add them together, we end up with 6 widgets. Very simple concept. Addition is just counting, basically. And subtraction is the same thing. If we said that we had 6 widgets and we sold 3 of them, we have 3 widgets left. And so basically we have 5, 6, and we sold we sold 3 widgets and they went off. And how many widgets do we have left? Well, we lost 3 from our inventory, and that means we have 3 left in inventory. So addition and subtraction is pretty much very straightforward. It's essentially counting and accounting. It's keeping track of quantities of things. Multiplication is just an enhanced form of addition. So when we say 2 times 5, 2 times 5, basically what we're talking about is we have two groups of 5. And those give us, when we add them together, we have 10. So 2 times 5 is 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. So basically, it's a shortened way of adding by groups. It's always by groups. So 3 times 6 times 6 are 3 groups of 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And that would be, if we count these, 18. This can also be read as 6 groups of 3. So we have 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And that's 1, 2, 3, 4, 5, 6 groups of 3. And when you count them, it comes up to 18. So adding and subtracting, multiplying and dividing are basically the same, except it's just a slightly different perspective, where adding and subtracting are direct counting. Multiplication and division are group counting. So rather than counting individual entities, multiplication is counting by groups. So, and usually the way they teach it in school is memorization. 1 times 1 is 1, the whole business. That little song, that little ditty. And people have been teaching addition, subtraction, multiplication, and division pretty much as a memorization thing for a long, long time. And I guess it has its benefits, because once it's drilled into your head, you basically have it there forever. But now we're going to look at what happens if we have powers, and we're going to be looking at exponents. So what if we have 2 by 2? Well, that means 2 groups of 2. 2 groups of 2. 3 by 3 equals 3 groups of 3. That's 3, 6, 9. This is 4. 4 by 4 equals 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 equals 16. So we have a notation for these types of things. We have, we say that this is 2 squared, or 3 squared. This is 4 squared. Oops. That's a square. And this is an equal sign. So we have a special notation that we give to multiplying quantities of the same number of units. So here, if we say we've got 2 to the 1, that means we only have 1 2. If we have 2 to the 0, that means we have basically just 1. Anything to the 0th power is 1. 2 squared is 2 times 2. 2 to the 3rd is equal to 2 times 2 times 2. 2 to the 4th is equal to 2 times 2 times 2 times 2. 2 to the 5th is 5 2's multiplied each other, and so on. 2 to the 6th equals 6 2's multiplied by each other. I think that's 6. And we can see that this is 4, this is 8, this is 16, this is 32, this is 64. And you can go on forever. So if we then say we have 2 squared times 2 to the 4th, that is, we have 1, 2, or let's put it this way, 2 times 2 times 4 2's. 2 times 2 times 2 times 2. Well, how many 2's do we have? We have 6 2's. That's 2 times 2 times 2 times 2 times 2 times 2. Let's see, 1, 2, 3, 4, 5. One too many 2's. Okay, so we can say that is 2 to the 6, because we have 6 2's. So we have 2 squared times 2 to the 4th equals 2 to the 6. And do you notice something? If we have the same base number, 2, this is where we get the name base, we have 2 plus 4 is 6. So this is the law of exponents. So if we have a base n to some power p times n to some power q, the result is n to the p plus q. And that is the law of exponents. So this is true for any base, but it has to be that the base is the same. If we have 2 squared times 5 squared, it's not 2 times 5 to the fourth or anything like that. It just doesn't make sense. This, when you work it out, is 2 times 2 times 5 times 5. So you can't add exponents when the bases are not the same. And so this here, we got 4 times 25, and that equals 100. So you have to be careful when you use the law of signs that the base is the same. So n to the p, where p is any integer, times n to the q is equal to n to the p plus q. And that's the law of exponents. Now, what if we had n to the p, n to the p plus n to the q? Is that equal to the n to the p plus q? No. And the reason for that is, let's give an explicit example. We'll stay with twos. Let's say 2 squared plus 2 to the fourth. Well, 2 squared is 2 times 2, but we're adding that. We're not multiplying. We're adding that to 2 times 2 times 2 times 2. And this is 4 plus, that's 16, and that's equal to 20. That's not equal to n to the, or let's say that is not equal to 2 to the 6, which is 2 times 2 times 2 times 2 times 2 times 2. This is 8 times 8 equals 64. So you can see there's a big difference. So you have to be careful with the law of exponents. It only applies to when the bases are the same and that they're multiplying one another. So that's the condition. The base has to be the same, and it has to be multiplication. Okay, that's very important. So one, base has to be the same. And two, and the bases are multiplied, not added. Okay, so those are the two conditions where this is true. Now, I want to give some examples of what we talk about. In our number system, we use what we call base 10. And base 10 means that when we write this number, let's say 5,462,328. Okay. This is 10 to the 0, that column. This column is 10 to the 1. This column is 10 squared. This column represents 10 to the 3rd. This column represents 10 to the 4th. This column is 10 to the 5th. And this column is 10 to the 6th. And we'll show how that works. So if we write, I lost my screen again. It's hard for me to see. I gotta adjust the screensaver at this point. Because it's nice to see what it is you'll be seeing. Okay. Now, what we do here is, let's say we write this 10 to the 0, 10, 1, 10, 2, 10 to the 3, 10 to the 4, 10 to the 5th, 10 to the 6th. And we remember what it means for that to be the power. This is equal to 1. This is equal to 10. This is equal to 10 times 10. This is equal to 10 times 10 times 10. And that's equal to 4 tens multiplied. And this one's equal to 5. And this one's equal to 6. All right. And that's equal to 1,000,000. This is equal to 100,000. This is equal to 10,000. This is equal to, oops, what am I doing? Equal to 1,000. When you multiply those out, that's 100. That's 10, and this is 1. So if we write out that column, as we did, each number here gets multiplied by that number there. So we have 1 times 8. Here we have 10 times 2. Here we have 100 times 3. Here we have 1,000 times 2. Here we have 10,000 times 6. Here we have 100,000 times 4. And here we have 1,000,000 times 5. And then what we do we add them up. So that's 8, that's 20, that's 300, that's 2,000, that's 60,000, that's 400,000, and this is 5 million. And if we add these up, that's 8, 2, 3, 2, 6, 4, 5. That's what this number represents. Well, not all numbers are in base 10. This is what we call base 10 because we're multiplying these integers against the power of 10 represented by that placeholder. Each position is a placeholder. This is a million placeholder, this is 100,000 placeholder, and so on. So that's what this means. If you then, let's say, I've got a number in base 5. Okay, so first off, when we write a number in base 5, we have to realize that let's say base 5. So our placeholders for base 5 that are permissible are 0, 1, 2, 3, and 4. So what if we have 4, 3, 2, 2, 0, 1, base 5. Well, basically this is like our base 10. We have 5 to the 0, 5 to the 1, 5 squared, etc. So what we do to convert this into base 10 is we draw 5 to the 0, 5, 1, 5 squared, 5 to the third, 5 to the fourth, and 5 to the fifth. And that's equal all right, we can find that. That's 1. This is 5. This is 25. And that's 125. And 125 times 4 is 20. 8, 10, 9. I just want to double check it. 20, 8, 10, or that's 500. I'm sorry. Where did I get 9? 500. It's always good to check things. 5 to the fourth is 25 times 25. That's 25, 10, 12, 10, or 5. So something I screwed up. Sorry. I'm not even going by my own definitions. I'm sorry. This is 5 times that. 125 times 5. 25. I may still be a little loopy from yesterday. 10, 12, 5, 6. That's 625. 625. And let me just double check that. 25, 10, 11, 12, 10, 4, 5. That's 5, 2, 6. Yep. All right. Sorry about that. Even I have trouble with numbers on occasion. So 625, and this one is 625 times 5. That's 25, 10, 12, 31. 3125. Let's just do it again to make sure. We got 625, 25 times 5, 25, 10, 12, 31. Okay, so we've got that correct. And then each placeholder here, that's times 1 times 0 times 2 times 2 times 3 and times 4. And this is equal to 1, 0, 2 times 25 is 50. Let's just put equal signs. That's 50. 125, 2, 10, 5, 250. Three times 625. So 625 times 3, 15, 6, 7, 18, 1875. Just make sure I got it right. 15, 6, 7, 18. Yep. And lastly, we got 4 times 3125. So 3125 times 4, that's 20. 8 is 10. 5 and 12. So that's 1, 2, 5, 0, 0. And now we add these up, and we find what base 10 is. All right, so 6, we have 10, 17, 10, 16, 4, and 1. So this number is equal to 14,676 base 10. And it makes sense because this appears larger than that because base 10 assumes a smaller value. Now, what if we were given this number and we wanted to convert it into base 5? Well, what we do is we do a lot of dividing. Again, we have 5 to the 0, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5. 3, 4, 5, 6. Yep, 1, 2, 3, 4, 5. Okay, we got the right ones. And what we do is we take 14,676 and we divide that by 5. So we got 2, 10, 4, carry that. That's 8, 40, 6, 7. Okay. Actually, we could have gone 9. 9 times 5 is 45. And that would have been 1. Carry the 7 down. 3, 15, 2, 6. We got 5, 25, and the remainder 1. So remainder equals 1. So we put the remainder over here. This remainder is multiplied by 5 to the 0. Now we take the $29, $35, and we divide that by 5. This is base 10. Okay, so we take the quotient and we divide it by 5 again. So 5 times 5 is 25, and that's 43 times 8, 40, 35, and we got 7, 35, and our remainder is 0. So this one gets multiplied by 0. Now we take our quotient, 587, and divide that by 5. That's 1, 0, 8. That's 1. 5. That's 3, 7. And so that's 7, 35, and the remainder is 2. So 2 gets multiplied there. And then we take our quotient again, 117. And we divide that by 5. We just keep doing this until we have nothing left. So that's 2, 10, 11, 17. That's 3, 15, 2. That's our remainder. So the remainder we put there. And we keep doing this. Okay. 5 into 23. Okay, this is 4 with a remainder of 3. So that remainder multiplies 5 to the 4. And we have 4 left over. That can't be divided anymore by 5, so we have 4 right there. So we've taken our number, 14,676 in base 10, and we've found its equivalent is 43221 base 5. And you can see that's what we had started with. So that's how we can go back and forth between different bases. But it's important here that you know that none of your placeholders can be, let's say in base 5, we can't have a base holder greater than 4. If it's base 7, we can't have a placeholder greater than 6. So let's try something like that. Let's look at another example. Let's say we are in base 7. That allows us to write numbers, placeholders, 1, 2, 3, 4, 5, and 6. And let's make it a little easier. Let's say this is 3, 140, 3140 in base 7. What would that be in base 10? Well, this is 7 to the 0, 7, 1, 7 squared, and 7 to the third. And that's equal to 1, 7, 49, and 49 times 7 is 63, 28, 34, 343. And I did that kind of quickly, so let me just check that. 49 times 7, that's 63, 28, 29, 30, 31, 32, 33, 34, 34. Okay, so now this is times 0 times 4 times 1 times 3. And this is equal to, that's 0, that's 28, this is 49, not 1, and 3 times 343 is 9, 12, 9, 10, 10, 29. So we add these up, and we have our number base 10. So we got 18, and 8 is 16, 26, 26. That's 6, 8, 10, 1106. Base 10. And that's how we convert it to base 10. So you can do that all day long. Those are how you convert to base 10. Now, converting back into base 7, we just take this, 1106, and we have 7 to the 0, 7, 1, 7 squared, 7 to the third, 343, 49, 7, 1. All right. Now we just take this and divide this by 7. And that goes, 7 into 1 goes, let's see, 7 into 11 goes once. 7, 4, 0. This goes 5 times, 35. And that's 5, 6, and that goes 8. 56 and 0. So 0 is our remainder. So that's 0. It corresponds with 0. Now we have 158 as our quotient. 158 divided by 7, that's 214, 118. All right, 3 is too big, 2, that's 14, and we got 4 there. That's our remainder 4, so that place corresponds with 4. We have 22 left. So we have 7 into 22, that goes 3, 21 with 1 left over, so that goes 1, and 3 goes there. So base 7, this is 3, 1, 4, 0, base 7. See, it's not so bad. It can be a bit time consuming. Now, one of our favorite bases is base 2. That is used very frequently in things like programming algorithms and such. So let's say base 2. What options does that give us? Well, 0 and 1. So if we have a number like 1, 0, 1, 0, 1, 1, base 2, what is that equivalent to in base 10? So this is 2 to the 0, 0, 1, 2, 3, 4, 5, 6. So we got to go 2 to the 6. 0, 2 to the 1, 2 squared, the 3, 2, 4, 2 to the 5th, 2 to the 6. And this is equal to 1, 2, 4, 8, 16, 32, 64. And here we have times 1, 1, 0, 1, 0, 1, 1. And that is equal, okay, this is 1, 2, 0, 8, 0, 32, and 64. And we add that together. And we got 8, 10, 14, 8, 14, 16, 17. And that's 10. So that's equal to 107 base 10. And what we can do to convert back is divide that by 2. Divide 107 by 2 and keep getting the remainders. So 107, 2, that's 5, 10, 0, 7, that's 3, 6, 1. So we got 1. These aren't really equal. We're just putting those as placeholders. Okay, so now we got 53. 53. 53, that's 2, 4, 1, 13, 6, 12, 1. So that goes 1. 26 divided by 2 is 1, 2, 0, 6, 3, 6, 0. So we have a 0 in that placeholder. 13 divided by 2 is 7. No. 6, 12, 1. We have a 1. 6 divided by 2 is 3. 6, 0. So we have another 0. 2 into 3 goes once. The remainder of 1, 1, and 1. So that's our number, base 2. We've converted from base 10 to base 2, so that would be 1, 1, 0, 1, 0, 1, 1. And that's exactly what we got. So that's pretty cool stuff. So we learned a couple of things today. We learned the law of exponents. So let's take a look at n times p to the 6th, and this is to the 5th, is equal to, well, it's certainly not n p to the 11th. That makes no sense. We have to, in order to use the law of exponents, we have to have the same base, and we don't have the same base. So here we have 6 n's, n times n times n times n times n times n times p times p times p times p times p, and that's it. That's the best we can do. I mean, that's n to the 6th times p to the 5th. But what if we had n to the 5th times n to the 12th? Well, we have the same bases, so we have multiplication, so we can apply the law of exponents. So that would be n to the 5 plus 12 equals n to the 17th. So we can apply the law of exponents here. Now, what if we had n to the 4th raised to the 2nd power? Well, what does that mean? That means we have n to the 4th times n to the 4th. And n to the 4th times n to the 4th means n to the 8th, or 4 plus 4 equals n to the 8th. So when we have a situation like this, where we have a power that's raised to another power, this is another law of exponents. When we have n to some power x raised to some power p, it's equal to n raised to the p times x. And let's take a look at it. So an example, 2 squared to the 3rd power. So this means we have 2 squared times 2 squared times 2 squared. All right. But that's equal to 2 to the 1, 2 plus 2 plus 2. And that is equal to 4, 5, 6, 2 to the 6th. And you can see that this is equal to 2 times 3, that exponent. And 2 to the 6th is equal to 2 times 2 times 2 times 2 times 2 times 2. And this is equal to, we got 8 times 8 equals 64. So this is another law of exponents. But remember, this is under the circumstance where we have a base that's raised to a power, raised to another power. So we have two laws of exponents now. We have this one, n to the q times n to the p is equal to n to the q plus p. And when we have n to the x raised to the p, we have n to the p times x. So we have two laws of exponents. And if I hadn't explained before, this is an exponent. That is an exponent. The power, an exponent, is the power to which a base number is raised. So those are two fundamental laws of exponents. And we'll be looking at exponents in a little bit more. But I just wanted to give you sort of a primer, an idea of what it means to be in a base. And in order to understand what it means to be in a base system, you have to understand exponents. So I hope this has been informative. It's not a very long video, but I think it is going a long way towards a fundamental understanding of what we're going to be looking at in the next few videos, exponents and logarithms. And logarithms are, you can think of them as inverse, or like arc tangent and arc sine. Well, they're the inverse functions for the powers. So anyway, this is Mathman wishing you all the well, all the best, and keep your heart healthy.